Welcome to the next class. In the seventh class, we'll discuss about the alternating current. Until now, we're discussing about the circuits which were excited by the constant or time invariant sources. It was because in in the beginning, DC sources were the main uh, sources which provides the power until late 1800s. At the end of that century, the battle between direct current versus alternating current started. It is actually the battle between Thomas Alva Edison and the Tesla. So, because of the AC, which is more efficient and economical to transmit over a long transmission line, and DC, which has a lot of losses and there is a lot of voltage drop in it. So, AC ended up in the as a winner. Thus, it is uh, thus in keeping with the historical sequence of events. That is why we considered the DC sources first or DC circuits first. Now we begin with the analysis of circuits in which the sources or voltage or current are time varying. In this chapter, we are particularly interested in sinusoidally time varying excitation, or simply they are called as sinusoids. What is a sinusoid? A sinusoid is a signal that has a form of sine or cosine function. That means voltage or current that vary uh, with time as a function of the sine or cos. A sinusoidal current is usually referred to as alternating current. It is actually the sinusoidal current finally which has retained as the name of the alternating current. There may be other alternating currents or alternating voltages which may alter with time, but the name alternating current here in circuit analysis is given to the current or voltage which are varying as sinusoidally. Such a current reversal at regular time intervals and has alternately positive and negative values. So that's why I told you this alternating positive and negative value can have any shape apart from this sinusoidal, but we have retained alternating current as a sinusoidal current. So circuits driven by the sinusoidal currents or voltage sources are called AC circuits. So this is simple. We are interested in the sinusoidal for a number of reasons. There are particular advantages. Why do we actually retain this alternating current as a sinusoidal current? First, nature itself is characteristically sinusoidal because all nature also swings back and forth from its two final positions. That's why nature also uh, prefers this sinusoidal. So, for example, we have a motion of a pendulum, the vibration of a string. You can see it is also sinusoidal. The ripples of the ocean going back and forth on the surface of the ocean, and the natural response of undamped second order system. These are some of the examples where you can see that the variation of the motion or the variation is of sinusoidal nature. Second is the sinusoidal signal is easy to generate and transmit. This is actually the most important, one of the second most important advantage of it. Uh, it is in the form of voltage generated throughout the world and supplied to homes, factories, laboratories, and so on. So the voltage that we uh, get in our homes is also sinusoidal. It is actually uh, supplied to every part of the world. So it is a dominant form of signal in communication and electrical power circuit. This is one more example application of this. And lastly, what personally I think is the most important thing about it is that the sinusoid is easy to handle mathematically. But how is it easy to handle mathematically? Because the derivative and the integral of sinusoid are themselves sinusoids. You can see we can have a change in magnitude and change in the phase angle, but you can see that by having a derivative or an integral, the shape of the signal retains because the derivative of the sine is cos, and the derivative of the sine is minus cos. Similarly, integration of the sine is minus cos, and the integration of the cos is sine. So what I mean to say is that mathematically, when we do the mathematical operation on them, they retain their original shape. We begin with the basic discussion of sinusoids and phasors, and then we introduce the concept of impedance and admittance. This is very important because phasors are important, and before phasors we need to understand what are different sinusoids and how they are then converted to the phasors. Let us start with the sinusoids. Consider a sinusoidal voltage, which is Vt is equal to Vm sine of omega t, where Vm is the amplitude or the maximum value of the sinusoid, or Vt. Omega is the angular frequency in radians per second, and omega t is the argument of the sinusoid or angle of the sinusoid. The sinusoid, as shown in 9.1a as a function of its argument and in 9.1b as a function of time, you can see over here, this is 9.1a and this is 9.1b. The x-axis over here is the argument in angle, and the x-axis over here is the argument, or we can say is time axis. Here it is the angle axis. It is evident that the sinusoid repeats itself every t seconds. You can see over here it repeats itself at every t seconds, or here it repeats itself at every 2 pi seconds. That means the time period of the sinusoid here is 2 pi. So, or this t is called the period of the sinusoid. From the two plots in the figure, we observe that omega t is equal to 2 pi. You can see over here that this is the time period, and this is actually omega t. When omega t is equal to 2 pi, here, when omega t is equal to 2 pi, that is one time period. That is omega into tau. Omega into capital T is equal to 2 pi. When this happens, that means this t is equal to 2 pi by omega. So this is the time period of the sinusoid, 2 pi divided by omega. The fact that Vt repeats itself every t seconds is shown by replacing t by t plus t, where t is actually it is time period. We get that is v of t plus t is equal to Vm sine of omega t plus t. So Vm sine of omega t, where t is equal to 2 pi by omega. So when we multiply this omega to whole of its angle, it will be omega t plus omega cancel plus 2 pi, and we know that sine of theta plus 2 pi is equal to sine of theta. It comes out again to be equal to Vm sine of omega t, that is Vt. So here in general, V of t plus capital T is equal to V of small t, that is V has a same value at t is equal to t plus capital T as it does at t, and Vt is said to be periodic. So in general, a periodic function is one that satisfies this equation, that is f of t is equal to f of t plus nt for all t and for all integers n. As mentioned, the period t of the periodic function is the time of one complete cycle, or the number of cycles per second, or we can say number of seconds per cycle. The reciprocal of the quantity is the number of cycles per second. So what is the time period? Time period is the number of seconds per cycle, how many seconds it takes in one cycle, and the reciprocal of it is the number of cycles per second, how many cycles it is completing in 1 second, and that is known as cyclic frequency. The reciprocal of this t is known as the cyclic frequency. Thus f is equal to 1 by t. From the equation 9.2 and 9.5, that is from here, this since t is equal to 2 pi by omega and f is equal to here, so t is equal to 1 by f, that means this omega will be equal to 2 pi f. That is what this equation means. While omega is in radians per second and frequency here is in hertz. Now let's now consider a more general form of expression of sinusoid. Let us say we have a Vt, which is equal to Vm sine of omega t plus phi. It has some phase difference from the origin, where omega t plus phi is the argument and phi is the phase. Both the argument and phase can be in radians or in degrees. So this is obvious. Let us examine the two sinusoids. That is, one is this and one is this. V1 is Vm sine of omega t. That means this is the sinusoid which started from the origin, and Vm is V2 t is equal to Vm sine of omega t plus phi. It means it started from omega t is equal to 0. Omega t plus phi is equal to 0. That means omega t is equal to minus phi. So it started before origin. You can see it from here. This V2 started from minus phi and V1 started from exactly at t is equal, omega t is equal to 0. These two are the two sinusoids. They have only the phase difference. They have the same amplitude, and they have the same. You can see the time period. The starting point of V2 in figure occurs first in time. The starting of this occurs first in time. That means this is leading this one, or we can say the peak of V2 comes before the peak of this V1. That means V2 is leading to this V1 by an angle of phi. Therefore, we can say V2 leads V1 by phi, or V1 lags V2 by phi, or we can say this V1. This is V1. It lags to V2 by phi. So I can say that the sinusoids which are on the right side of which are on the right side to the left of any sinusoids. The sinusoids which are on the right side are lagging, and the sinusoids which are on the left side are leading. You can see it from here. V2 is on the left side of this, it is leading to this, or we can say V1 is to the right of this, or we can say it is lagging to V2. If phi is 0, then V1 and V2 are said to be in phase. If they are in 0, you will see that as if there is only one sinusoid if they have the same peak. They reach their maxima and minima at exactly the same time. In that case, maxima and minima, they will have the same time, and they will also touch the 0 or cross the 0 at the same time. We can compare V1 and V2 in the manner because they operate at the same frequency. This is very important because when they have the same frequency, we can compare them. If the frequency changes, it's very difficult to compare these sinusoids. They do not need to have the same amplitude. Even if the amplitude is different, the frequency is same, then it is very simple to compare them. But here the prerequisite is the same frequency. Now a sinusoid can be expressed in terms of sine or cosine. When comparing the two sinusoids, it is very important to express both either sine or cos, and then it is very easy to compare them, and also their amplitude should be positive. So there are some identities in terms of sine and cos which can help us to achieve this. We can change the cos to sine. We can change the sign of the sine of the sine. Sine means we can change the whether positive sign or negative sign of the sine or cos to other this negative sign or negative to positive sign. So one identity is this: sine a plus minus b is equal to sine a cos b plus minus cos a sine b. That means when here it is plus, here also we have to use plus. Similarly, cos a plus b we can use here at cos a cos b minus plus sine a sine b. When here it is plus, here we have to use minus, and when here it is minus, here we have to use plus. One more identity that we can use to absorb sine of the cosine of the sinusoid, that is this: sine omega t plus minus at will be equal to minus sine 80, cos plus minus 180 is equal to minus cos 80, and sine omega t plus minus 90 is equal to plus minus cos of omega t. Plus, when plus is used over here, it will be here plus. When minus is used over here, it will be minus. Similarly, cos plus minus 90 is a minus plus sine of 90. Mostly we are using these identities as compared to these identities, but sometimes we may have to use these identities as well. One more important thing is that the graphical representation of the sinusoids. A graphical approach may be used to lead the compare sinusoids as an alternative to the use of trigonometric functions. If you are not able to understand or remember these trigonometric identities, we can use the graphical approach. The horizontal axis represents the magnitude of cosines. This represents the magnitude of the cosine, while the vertical axis denotes the magnitude of sine, but it is pointing downwards. This is the sine wave. Angles are measured positively counterclockwise. That is the usual trend. Counterclockwise angles are to be taken as positive, and clockwise angles are taken to be negative. This graphical technique can be used to relate to sine. For example, if we see that subtracting a 90-degree from an argument of cosine gives a sine. You can see from here this cos of omega t minus 90. That means we are actually subtracting 90 degrees from the argument of cos. It will give us plus sine omega t. So you can see it from here. When I subtract, that means I have to go to the clockwise. From this to this, I will reach to the sine omega t. So in this way, it will help us to understand when we change cos to sine or sine to cos, what are the different angles that are to be added or subtracted. So one more thing. Similarly, adding 180 to the argument of sine of omega t gives minus sine omega t, because when I add 180 to this sine omega t, I have to add it counterclockwise. I will reach to this axis, and this is the minus sine omega t. That is what is this shown by this. That is whether subtracting or adding, you will come to minus sine of omega t. So this is subtracting will be in this way, and you reach the same place. That is why it will be minus sine omega t. Now, a graphical technique can also be used to add two sinusoids of the same frequency when one is in the form of sine and another is in the form of the cosine. To add a cos omega t and b sin omega t, we know that a is the amplitude of the cos omega t and b is the magnitude of the sine omega t. As shown in figure 9.4, you can see from here, we have this is a cos omega t and b cos omega t. We can use graphically to add them. The magnitude of the argument of the resultant sinusoid is in cosine form is readily obtained from the triangle. You can see it from here. That means a cos omega t plus b sin omega t is equal to c cos of omega t minus theta. You can see it over here. We have c cos omega t minus theta. What is the value of actually c? C is equal to root of a square plus b square, where theta is equal to tan inverse of b by a. Tan inverse of b by a. You can get it from here. This is theta. This is its perpendicular. This is b base. So tan theta is equal to perpendicular divided by base, or theta is equal to tan inverse of this perpendicular divided by base. Perpendicular is b and base is this. And this c is equal to this square plus this square. So similarly, we can be using this. For example, if we have a 3 cos omega t and minus 4 sin omega t. So to calculate uh, to add these two sinusoids, so this will be the final result of, or we can say magnitude of the two sinusoids. That means 5 will be equal to square root of 4 square plus 3 square, and this angle will be equal to tan inverse of this 4 divided by 3. So in that case, it is simply very easy to add the two sinusoids. Okay. Now, for example, this is the same thing. We have to add 3 cos omega t and minus 4 sin omega t. We get this. Compared with the trigonometric identities in equation 9.9, and the graphical approach eliminates memorization. So that is what I have told you. If you don't remember this, you can use the graphical approach to calculate the final result. However, we must not confuse the sine and cosine axes with the axes for complex numbers to be discussed in the next section. So because these phasors may be represented in terms of complex numbers, but I will not go into the details of complex numbers. Something else to note that although the nature tendency is to have the vertical axis pointing, the positive direction of the sine function is downwards. In the present case, we have used the positive axis of the sine axis to downward. It is because it makes our thinking, and it makes our analysis is very simple as compared to taking the upward axis as the positive axis. Now let us try to do the same thing. We'll have some small types of numericals to understand the concept of sinusoids. Find the amplitude, phase, time period, and the frequency of the sinusoid, which is given as Vt is equal to 12 cos of 50t plus 10. Here it is very simple. Whatever is multiplication of this cos omega cos of the argument, this will be its amplitude. That means the amplitude is Vm. 12 is Vm is equal to 12 volts. Since its unit will be 12 volts, volts, so we have to use the 12. And this will be omega t plus theta. So phi will be equal to 10. Omega t plus phi, it will be 10. The angular frequency omega is 50 because this is omega tt is given over here. That means this is omega. Omega is 50 radians per second. The time period will be equal to 2 pi by omega. That is 2 pi by 50. It comes out to be 0.1257 seconds. And the frequency is 1 by t. That is the reciprocal of this. That is 7.958 hertz. This is how we can calculate the different parameters of a sinusoid. So one more thing, calculate the phase angle between V1, that is minus 10 cos of omega t plus 50, and V2 is sine 12 sine omega t minus 10. So I have told you that the first thing that you have to ensure that the two phasors or two sinusoids have the same frequency. So it is given it is omega, that means they have the same frequency. After that, by using the different identities, or you can the phasor graphical approach, you can simply calculate their phase difference. First we'll use the trigonometric identities. So why I have to use the trigonometric identities? Because here it is minus, we have to convert it to plus, and here the two terms are sine and cosine, we have to convert them to either of the one. That is, either we have to convert this to cos and we have to convert this to, this is already in the cos, but we have to change it to sine without actually affecting the actual value. So let us start with the method 1. In order to compare V1 and V2, we must express them in the same form. If we express them in the cosine form with the positive amplitude, so V1 is equal to minus 10 cos of omega t plus 50, it is given. So I will add or subtract this. I have to add minus 180 degree to get the plus cos. You can see over here. Yes, here. You have to subtract 180 degree, or you have to add 180 degree to get the minus cos. So in that case, minus will be consumed here. So here it has been done that this angle has been subtracted. So I got it over here. V1 is equal to 10 cos of omega t minus 30, or V1 is equal to 10 cos omega t plus 230 when you add 180 degrees. Subtracting, you get this. Adding, you get this. This and this is the same thing. Similarly, V2, 10 sine omega t minus 10, 12 sine omega t minus 10, 12 cos of omega t minus 10 minus 90. Actually, I have subtracted minus 90 to this cos, I will get sine. We have seen it from the graphical approach. So it comes out to be equal to V2 is equal to 12 cos of omega t minus 100. So it can be deduced from equation 9 that the phase difference between V1 and V2 is 30 degrees. You can see it from here. It is omega t minus 130 degree. It is omega t minus 100 degrees. So from here to here, you can see the phase difference is 130 degrees. Sorry, it will be only 30 degrees. So that's why it has shown both the phasors in terms of this and in terms of this. The phase angle over here would have been positive, then you will definitely use this positive difference in the positive angle. So now let us try to do this graphically. What will we do in this graphical case? And one more thing here, you can see it here. So this V1 is lagging to the cos axis by 130 degree. It is lagging to the cos axis by 100 degrees. So the leading phase will be having this. So that means V2 will be leading to this V1 by 30 degrees. Now coming to graphical approach, we may regard V1 as simply minus 10 cos of omega t with a phase shift of plus 50 degrees. So this is the plus cos axis, this will be the minus cos axis, and plus angle. We have to add the 50 degrees in counterclockwise direction. So we'll start from here and reach over here and we end up 50 degrees. So this will be V1. Similarly, what is the next one? Is it shown or not? Similarly, V2, that is 12 sine omega t. This is 12 sine omega t with minus 10 angle. So this is sine omega t axis, 12 sine omega t will be in this direction and minus 10. It has to subtract angle in clockwise direction. That means it goes to this direction. So this is 10 degree, this is 50 degree. Total from here to here is 90 degree. You can see the phase difference between these two will be 30 degrees. So this approach also we can use and to help the understanding the comparing different sinusoids. So now let us come to the phasors. Actually, these phasors are derived from their sinusoids and they are very simple as compared to the sinusoids. Sinusoids are easily expressed in terms of phasors, which are more convenient to work with than sine or cosine functions. So here, actually, we are dropping the sine and cosine function. We are directly uh, taking only some information from the signal, not all the information. A phasor is a complex number that represents amplitude and the phase of a sinusoid. It only takes two things from the sinusoid, that is phase and amplitude. It forgets about the frequency and the time period. So when you use the phasors, or when you compare the two phasors, the prime implication or the prime requisite is that they have the same frequency. When they have the same frequency, you have to forget about these things and you have to just care about the amplitude and the phase of the sinusoid. Phasors provide a simple means of analyzing linear circuits excited by the sinusoidal sources. That's why we go for the phasor analysis. Solution of such circuits could be very difficult otherwise. So if you don't use the phasors, you can still solve them, but the solution will be very difficult. The notation of solving the AC circuit using phasor was first introduced by the Charles Steinmetz in 1893. So this is a slight history regarding the phasors. Now coming to this, the idea of the phasor representation is based on the Euler's identity. It is very important and you have to remember this, that e raised power plus minus j phi is equal to cos of phi plus minus j sine of phi. This is very important and the basis of the phasors lies on this equation. So that means when here is plus, we have to use it. That's e raised power j phi is equal to cos phi plus j sine phi, e raised power minus j phi is equal to cos phi minus j sine phi. So we show that we may regard cos phi and sin phi as a real and imaginary part of e raised power j phi. We may write them that cos phi is the real part, r is the real part of e raised power j phi. You can see from here, if we use only plus over here, it is e raised power j phi cos of phi plus j sine of phi. So the real part of this e raised power j phi will be cos of phi. Similarly, imaginary part of this e raised power j phi will be sine of phi. So we can represent cos of phi and sine of phi in terms of these equations. Now we'll use the same thing, that is these two equations, to actually derive the phasor from the sinusoid. So given the sinusoid Vt is equal to Vm cos of omega t plus phi, we use equation 9.28 to express Vt as Vt is equal to Vm cos of omega t plus phi, which is actually the real part of e raised power j omega t plus phi. Here we have the whole angle as omega t plus phi. In this case, we have only angle as phi. So that's why. So we have to take this as in this manner, that e raised power j omega t plus phi. So Vt we can represent as Vt is equal to Vm e raised power j phi into j e raised power j omega t. Actually, this it will be equal to e raised power j omega t plus j phi. So when you have some exponents which are added, we can simply separate them by having multiplication of these two terms like this: e raised power j phi into e raised power j omega t. When bases are same, that is e power should be added. We get again the same thing. So since I have told you when we use the phasor, I'll first combine these two things: Vm e raised power j phi So this will be equal to v of t is equal to real part of v e raised power j omega t. So where v is equal to this term, which is we do not have any component like time and frequency, you can see over here. So this v is equal to vm e raised power j phi, or we can write it as vm at an angle of phi, where angle phi gives me is given from this angle. So this is actually the phasor representation of this sinusoid, where we omit the frequency and time, we only take the this maximum value or amplitude and the phase angle. So this V is thus the phasor representation of sinusoid Vt. A phasor may be regarded as the mathematical equivalent of a sinusoid with same time dependency, with the time dependency drop that I have told you. In other words, a phasor is a complex representation of the magnitude and the phase of the sinusoid. To obtain the sinusoid corresponding to a given phasor V, multiply the phasor by the time factor e raised power j omega t and take the real part. So what I mean to say is from this sentence that if you are asked to find out the real part, sorry, exact sine omega t, this sinusoid, you just have to multiply this term again, e raised power j omega t, which we have just dropped, and then take the real part of the complex number. You will get the actual sinusoid. Since the phasor has a magnitude and phase, that is direction, it behaves as a vector and is printed in the bold face. So yeah, in respect to the vector, it has also magnitude and a phase, so it behaves like a vector in that perspective. For example, if we have a phasor Vm angle of phi and Im angle of minus theta, and you can see how they are graphically plotted. Let us say this is the real axis, this is the imaginary axis of a complex number. So Vm angle of phi will be like this, because when you use the rectangular form of this complex number, it will be equal to Vm cos of phi. You can see it here. This is actually Vm angle of phi is actually Vm, this e raised power j phi, it will be equal to Vm cos of phi plus j sine of phi, or we can say Vm cos of phi plus j Vm sine of phi. So you can see from here, this Vm cos of phi will be on this real axis, and Vm sine of phi will be on this axis, and total Vm will be the phasor sum of this, or we can say vector sum of this for the time being. Similarly, for this case, you will have, this will be Im angle of theta, it will be Im e raised power minus j theta. So e raised power minus j theta will be equal to cos of theta minus j sine of theta. Cos of theta will be in this direction and minus j sine of theta will be in this direction. This is the complex notation. So the total summation will be in this direction. So in general, you will see that most of the phasors which have a plus angle will be in the first quadrant, and most of the phasors which have a negative angle will be in the fourth quadrant. Now, to get the phasor corresponding to sinusoid, what we do, we first express the sinusoid in terms of cosine form, so that the sinusoid can be written as a real part of the complex number. That is like this. Like this. We have to write it in this form. Then we take out the time factor, and whatever is left is the phasor corresponding to the sinusoid. That means then when we get this, we drop out this the time factor, and we get this, which is the phasor. By suppressing the time factor, we transform the sinusoid from the time domain to phasor domain. We are changing. So when we suppress this time factor, we change, or we shift from one domain, that is the time domain, to another domain, that is the phasor domain. The transformation is like this: Vm cos of omega t plus phi is the time domain representation, and when we change to phasor domain representation, we write it in this form, that is V is equal to Vm angle of phi, that is the phasor domain representation. So sinusoids with different representations can be shown like this: Vm cos of omega t plus phi will be Vm cos of phi. So Vm sine of omega t plus theta will be equal to Vm phi minus 90, because when we use the reference as a cos, this will be lagging to this cos by 90 degree. You have seen it graphical approach. We have to change this sine to cos by simply by subtracting 90 degree to this, we'll get the cos. So it means it will be equal to Vm phi minus 90. Im cos of omega t plus theta will be equal to Im angle of theta, and Im sine of omega t minus plus theta will be equal to Im theta minus 90. This is a table just to remember you. If you have any problem, you can directly use otherwise the graphical approach or the trigonometric identity to get these values, because this will be equal to Vm cos of omega t plus phi minus 90, and finally it comes out with this. The frequency is not explicitly shown in the phasor domain representation because it is assumed that it is constant. However, the response depends on for this reason the phasor domain is also known as the frequency domain. But the response finally depends upon this frequency. If the frequency changes, its response may change, and that is why it is usually known as the frequency domain. We don't have to go down there, you just have to see this what will happen. One more important thing is the mathematical derivation. So I told you that this is actually the sinusoid advantage, and the phasors inherit that advantage from the sinusoid. That is the mathematical ease. So let us try to multiply this sinusoid, which is originally equal to Vm cos of omega t plus phi. Sorry, have a derivative of it. So dv by dt is equal to minus omega Vm sine of omega t plus phi. This is the derivative of this. So I can write it in terms of cos again. It will be equal to omega Vm cos of omega t plus phi plus 90 degrees. So I can write it in terms of the Sinusoidal identity, real part of omega Vm e raised power j omega t e raised power j phi e raised power j 90. So when you simplify e raised power j 90, it will be equal to j cos of 90 plus, sorry, it will be equal to cos of 90 plus j sine of 90. Cos of 90 is 0, j sine of 90 will be equal to j. That's why we have written over only j. So here it is omega. So it will be equal to this j into omega. Vm e raised power j phi will be equal to v, and e raised power j omega t is as it is. So that means this shows that a derivative of Vt is transformed into the phasor domain as j omega v. You can see j omega v, the rest remains the same. So when I have a derivative of any phasor, so I just have to multiply j omega to the actual phasor to get its derivative. That means dv by dt in time domain is equal to j omega v in the phasor domain. Similarly, in integral form, you can transform this integral of v of d in time domain. It will be divided by j omega will be divided because it is the opposite of the differential. So differentiating a sinusoid is equivalent to multiplying its corresponding phasor by j omega. Integrating a sinusoid is equivalent to dividing the corresponding phasor by j omega. So in this way, this is very simple. You don't have to actually change this actual phasor. You just have to multiply some other factor to get converted into derivative or an integrator. So the difference between v and v should be emphasized. This is very important. Vt is the instantaneous or the time domain representation, while v is the frequency or the phasor domain representation. This is one. Vt is a time dependent, while v is not time. Capital V is not a time dependent. This is the fact often forgotten by the students. This is very important. Vt is always real with no complex term, while v is generally a complex number. Finally, we should bear in mind that the phasor analysis applies only when the frequency is constant. I'm telling it again, time and again. It applies in manipulating the two or more sinusoidal signals if they have the same frequency. So when you manipulate or compare the two or add the two sinusoids with the same frequency, this phasor becomes very easy. Now let us try to do some numericals to understand it properly. We have I is equal to 6 cos of 50t minus 40, and V is equal to minus 4 sine of 30t plus 50. We have to change it to phasor. This is very simple. It is in the standard form. This will be equal to 6 at an angle of minus 40. There is no change. But here we have to change here. So minus sine of A is equal to cos of A plus 90 degree. That means we have to add 90 degree to this. So minus cos of 30t plus 50, that is the actual phasor, it will be equal to minus cos of 30t plus 50 plus 90. It will be equal to 4 cos of 30t plus 140 degree. It is equal to 4 at an angle of 140 degrees. So This way you can convert a sinusoid into a phasor. Now the reverse, find a sinusoid representation represented by these phasors. This is minus 3 plus 4j. This is j8 e raised power j20. So I is equal to minus 3 plus j40. So transform this into time domain. It will be equal to 5 at an angle of 126. That means you have to add them. How to add them? So you will get this 5 has come out from here, so getting the square root of this plus this, and angle will be equal to minus 5 will be equal to tan inverse of this and this. Since 5 is minus, you will get a plus 5 over here. That comes out to be equal to 126 degrees. So transform this in time. Now transform this in time domain. This is 5 cos omega t plus this angle. So this, then it's very simple. Now this quantity, this is j. Since j is equal to 1 angle 90, you can see it here. J is equal to 1 angle 90. This is equal to 1 e raised power j90. That is equal to 1 cos of 90 plus j sine of 90. That comes out to be j. That means we can represent j is equal to 1 angle of 90 degree. So this term will be equal to j8 of this minus 90 degrees, sorry, minus 20 degrees. So j has been again, this 1 angle 90 has been replaced for j. 1 angle 90 degrees into 8 angle 20 degree, and we know from the complex notation, when two complex numbers are multiplied, their magnitudes are multiplied and angles are added or subtracted depending upon their sign. Since here they are of opposite sign, they have to be subtracted. It comes out to be equal to 8 angle of 70 degrees. So converting them into time domain, it comes out to be equal to 8 cos of omega t plus 70 degrees. So this is how these two can be done. So we have to find the sum of these two terms. That means 5 cos of omega t plus 30 and 4 cos of omega t plus 30 and 5 cos of omega t minus 20 degrees. So we convert them into phasors, and a bold letter phasor I5 is equal to 4 cos of 30 degrees, and I2 5 cos of omega t minus, I have subtracted 90 degree to this to get this cos term, to actually consume this, yes, to get the cos term. So it comes out to be 5 cos of omega t minus 110. It will be equal to I2 is equal to 5 at an angle minus 110. So this will be 4 angle 30 plus 5 angle minus 110 degrees. So 4 angle, converting them into the rectangle form of complex number, it will be 4 cos of 30 degrees plus 4 sine of 30 degrees. That is this term, and this term will be 5 cos of 100 minus 110 degrees, and then this j 5 sine of 110. It will be this. Then adding real and imaginary part, you will get this value. Adding real and actually summing real and imaginary part, this has to be added to this, and this has to be added to this. You will get this value. So finally combining it to the phasor value, that means getting square root of this plus this, and then angle, you will get this value. So this is how the two sinusoids are converted into phasors, and then they are added. One more important thing is to solve the differential equation. Using the phasor approach, determine the IT in the circuit described by the into differential equation. This is an into differential equation. It's not a totally differential equation, but you can use this for a differential equation also, because you have to differentiate it again to convert it into a differential equation. So we transform it into the phasor. Let us say when we transform this into phasor, it comes out to be 4i, and when you transform this into the phasor, it will be equal to 8i divided by j omega. 8 is there, and converting this into the phasor, you know that we have simply divided by j omega. For this also, we have to, for a derivative case, we have to multiply the j omega, and this will be like this. This comes out to be, this is simple, 5 at an angle of 75. Taking I as a comma, it will be 4 plus 8 by j omega minus 3j omega I, and you can see from here omega is equal to 2. That is for omega has been taken as to 2. That means 8 by j, this is 4. 8 by j omega is equal to minus j4, because 8 by 2 is 4 and 1 by j is equal to minus j, and this is 3 into 2 will be equal to 6j. That comes out to be this. This will be 4 minus 10j. So finally I will be equal to this divided by this whole term, that is 50 divided by 4 minus 10j, that is 50 divided by 10 plus 10.77 at an angle of 68.2 degrees. So these two will be when the complex numbers are in polar form and they are to be divided. So their magnitudes are divided and their angles are to be subtracted. So 50 divided by 10.77 is equal to 4.642, and this angle, when they are subtracted, they will get added 143.2. So converting that time domain again, it will be equal to 4.642 cos of 2t plus 143.2 dt. This is how you can use this. So I will give you some homework over here. Find the phase angle between this and this, and then finally you have to tell whether I1 leads or lags to I2. If V1 is equal to this and V2 is equal to this, find V1 plus V2. Find the sinusoids corresponding to phasors this and this, and finally find the Vt whose circuit is described by this intro differential equation by this form. So I think this is it for today. Thank you very much.